So the agenda for this classical substation training is to give you a background of substation automation. How did it start in the history? How did substations evolve? Where did the idea of substations came from, and how the communication protocol started to develop in substation design, and what are the utilities requirements that have impacted the communication protocols in a substation and its development over the years, all the way up to starting 61850 in the next section. Thanks. So the idea of AC substation generation and transformation came about in the 1890s. Basically, there was a little AC-DC competition going on between Thomas Edison and George Westinghouse, and the idea was that George Westinghouse was pushing for the AC setup, while Thomas Edison has a great investment in the DC power. At the end, in 1893, Niagara Falls Power Company, NFPC, was finally convinced by George Forbes to award the contract to Westinghouse. Power was to be generated and transmitted as alternating current at a frequency of 25 Hertz to minimize impedance loss in transmission. 1892, General Electric has reformed and immediately invested heavily in the AC power. General Electric hired many great talents and engineers to improve the design of the transformers, generators, motors, and apparatus for alternating current transmission networks. Today they provide redundant paths and lines of powers to greatly improve the stability of an AC network. It was soon discovered that turbines would start to produce more power with less material investment. So great investors like Insuls basically started to place orders on General Electric. So 1903 was the first order that was placed on General Electric to provide the first turbine for basically producing 5,000 kilowatts or 5 megawatts of power to be used in the market. Pleased with the unit performance, he ordered another turbine that would generate 12 megawatts in 1911. Using these turbines and decreasing the cost on power reaching the end users, started basically the market for competition for all the electricity production and delivery to clients or end customers in the market and users. So in 1907, the companies started to produce somewhere around 5.9 million kilowatts to 75.4 million kilowatts in 1927. So 1927, we've seen the 75.4 million kilowatts. As such, the standards or the requirements for substations has started to appear in the market. With the advent of power systems, we started to see electrical utility show up. An electrical utility is an electric power company, as you know, that's responsible for the generation, transmission, and distribution of electricity for sale generally in a regulated market. After the electrical utilities, which were showing up in separate areas, we're starting to see the development of electrical utilities that are interconnected. So these will be responsible for transmission, distribution, and generation of power, but also will have communication and dispatch centers that are intercommunicating in order to provide power to the end users. The complexity in the system started to show up. So if we want to summarize what are the utility needs, first is to establish reliable power delivery to consumers. whether those consumers are industrial, commercial, or residential. Second is to manage all commercial aspects relating to selling or buying of electricity. Third is to allow for the grid to expand and plan expansion of the grid. The challenges of a utility would, if we like to summarize it, it would be to minimize the cost of delivery. So that's a prime for any utility, whether it is governmental owned or a government utility or a private utility. The main goal will be to minimize the cost of delivery. The second is to basically manage the outages and meet the restoration regulations for power. For example, if it is to be power is to be restored in 24 hours between December 31st and March 31st. So this would be a type of a regulation that power utilities would have to make sure that they meet it. Third is to minimize non-technical losses. Non-technical losses is a loss not due to a failure in one part of the grid, but more it's an induced loss by an external entity to the power grid. So this would be a quick summary of the utility needs and challenges. To analyze substations, we can categorize substations based on their voltage level, the type of insulation that they use, or by the structures that are used in the substation. These elements are not disjoints, or these classifications are not disjoint. They basically work hand in hand in order to resolve a transmission issue. You might use a lot of distribution functions. So, for example, let's say that we want to classify the substations based on their voltage levels. You would have a transmission substation, a distribution substation, collector substation, a switching substation, generation substation. So 5 types of substations that are basically defined based on their voltage level and how the power is transmitted in them. If I want to basically classify the substations based on their insulation, we could have an air insulated switchyard, AIS, or gas insulated switchgear or switchyard, which is GIS. If I want to say what's the type of substations based on structures, you can have an outdoor above ground substation or an indoor underground substation. So either outdoor or indoor, above ground or underground, all of this would play basically in the classification of our substation. So the parts of a substation, if we want to take it into take the primary parts of a substation, you will have a switchgear, transformer, your incoming feeder, outgoing feeder. You'll have your switches, and then there will be metering, capacitor banks, and then there will be a lot of ancillary or extra devices that are basically monitoring. So there will be a local HMI, there will be basically a communication platform, a GPS clock system, an alarm logging system. So all of these extra devices that are built around the primary devices in order to allow for remote communication or remote monitoring of a substation would also play a role in the classification of a substation. Okay, there is many ways to describe today's electrical grid, and in the electrical grid, as we said, there is many utilities. These utilities exchange power in the market. So the market in the picture, as you can see, is where power gets exchanged, sold, taken. The utility doesn't always take or buy power because it's not generating enough power. Sometimes it is economically beneficial to go buy electricity from another utility, because that utility is producing power at a cheaper cost. Maybe they have hydropower versus fossil power, and we'll talk about that in the coming up PowerPoint presentations. As you can see in the picture, there is generation utilities, there is transmission utilities, distribution utilities. A utility can be occupying any of these entities. So we could have a utility that's both a generation and a transmission utility, or a utility that is a transmission and a distribution utility. At the end of the day, this entire system is set up in order to deliver electricity to the end customer. And the customer in the old days used to request all the services from the utilities. Well, today the setup has changed. They can get their electricity service support from an independent service provider. For example, a service provider who's selling solar panels that is going to be installed on the top of the houses and provide a separate power input to the house from the installed electrical grid. And not only that, but you could sell back electricity to the electrical grid. Like if you have a farm and you get one of those wind turbines in your farm and you want to sell back to the grid, then you would need an independent supplier or an independent service provider who's willing to come, install it, and let you do this job. So all of this is being controlled at the end of the day by, as you can see in the picture, the operations. So the operations is monitoring the full system, is monitoring what is being exchanged in power in the markets, what's being done at the transmission, generation, distribution, and by the service providers. And it all shows up in the human-machine interface, or HMI, of the operations team to control our grid today. Okay, so the first application in our model here, in this NIST model, is the generation application. And under the generation application, we're basically taking a different source of energy and we are converting that different source of energy to electricity. The sources of energy is categorized as variable and renewable, or non-variable, non-renewable. A variable, it means that you don't have a continuous supply of energy, versus a non-variable, which is has a continuous supply of energy. So for example, a variable, as you can see in the picture, would be the sun, the wind. All of these will give you variable power supply. A non-variable would be a continuous power supply, example, the water, uranium, and all of these. Renewable and non-renewable, it means the source of energy can be replenished. It means it's renewable. Non-renewable, it means the source of energy cannot be replenished. So let's go quickly through what you can see here in the picture. So we've got the solar and the wind, and those are renewable variable. So the source of power can be renewed. At the same time, the power is available whenever we have sun and whenever we have wind. Next, we have the hydro, the biomass, the geothermal, and the pump storage. The hydro is basically waterfall, which would provide us with non-variable renewable source of power. The biomass is basically trees or green power, sugar cane, and all of that. Geothermal is power based on the heat from the earth. And pump storage is the idea of using excess power in order to pump water upstream that will get stored so that it can be used later, like the hydropower, in order to generate electricity downstream. Okay, and the last category is the non-renewable and non-variable. In this case, we've got the nuclear, the coal, and the gas. Some of the key performance and the quality issues of the generation is the scarcity of fuel and the generator failure, both of which require a lot of communication, routing into the transmission lines of power, so that we reroute the power to get it either from a different market or via other means. All of it puts decision in the operator of the generation system. So the operations domain have to make a decision as to what power gets generated based on what source, and how can they meet the demand of the transmission requirements. Next is transmission. Transmission basically is the bulk transfer of power from generation to distribution through multiple substations. So most of the activity is taking places in the substation. These activity or these operations are basically controlled by an operator through either a regional transmission operator or an independent system operator, RTO or ISO, whose primary responsibility is to maintain the stability of the electrical grid, balancing generation, which is supply, and the load, which is the demand at the end customer. The transmission domain contains distributed energy resources such as electrical storage or peaking generation units. Most of the action or most of the application is being done in the substations, and it's all utilizing the entire network of transmission is utilizing the supervisory control and data acquisition or SCADA systems, which is composed of a communication network, monitoring devices and control devices. As an example of a transmission domain unit, we have the remote terminal unit or the RTU, substation meters, protection relays, power quality monitors, phasor measurement units or PMUs, SAG monitors, fault recorders, substation user interface. All of this perform applications that are, as you can see, that's shown in your in the picture, which is, for example, to control, measure, protect, record, stabilize, and optimize the delivery of power from the generation to the distribution. Okay, next we're going to talk about the distribution. As you can see, the distribution is between the transmission and the customer domain. The distribution domain was historically in a tree setup. There is many types or variable types of distribution. There is trees, loops, and parallel paths. The idea of distribution is to take the power or the electricity from the transmission through a substation or through a distribution substation and then convert it to a low voltage that can reach to the customers. Historically, with the tree-shaped installed, there wasn't a lot of sensors in the distribution domain, and basically the best sensor that was available was the customer with a phone waiting for a dispatched person to come and resolve his problem on the network. Today, with the availability of all the sensors and all the detection, we have given rise to the microgrids, that when a problem occurs, these microgrids can resolve the problem even without customer notice sometimes. From a distribution domain, we have the main items include capacitor banks, sectionalizers, reclosers, protection relays, storage devices, and distributed generation. For example, like if you've got a wind turbine that's at the customer side, not only power coming from the transmission lines. All of this is to, of course, again, support the same, in the same manner and the same idea as I've talked in the transmission. Basically, as you can see in the picture, the control, measure, protect, record, and optimization of power in the distribution domain. The customer domain consists of the idea of managing the customer requirements and managing the customer information. So the limits of the customer domain is normally the meter, and as you can see, we have 3 customer domains, 3 types of customers, basically the home, the industrial, and the building. The home is normally around 20 kilowatts. The building is around, building or commercial is about 20 to 200 kilowatts, and above 200 kilowatts would be an industrial customer. And all the information is being electronically stored. So we have an electronically stored information that's being communicated from the meters using an advanced meter infrastructure or AMI setup. And the information normally resides inside the meter. This electronically stored information resides in the meter, which basically allow us to put more applications for the customer. For example, remote load control, so somebody can turn off, turn on certain devices for the customer based on the load and the load cost. Or the customer himself might want to control his load usage based on the availability of certain tariffs. So he would turn on, turn off some loads based on the cost, the per hour cost, monitoring and control of distributed generations, in-home displays that will show the customer usage. All of this is enabled through the storage of this electronic information that's also being used by the operations and by the dispatched or the service providers in order to make sure that the customer receive reliable and optimal energy. So far we have covered the generation and the generation markets, the transmission, the distribution, the customers domain. All of this is being managed by the operations, and the operations have many tools and utilities that are defined by and regulated by many IEC standards. Example, IEC 61968 standard, which is the interface reference model for the operation domain. But at the end of the day, whatever the operations decision is, we normally find many parts, as you can see in the picture, that are responsible for different aspects of the operation. So for example, you have an energy management system, which basically controls generation and generation power. You have a DMS, a distribution management system. That basically controls the distribution power and managing the customer outages. In case an outage, the customer have an outage. There's also an outage management system, an OMS. You can add to that GIS, CIS, LMS. All of these different acronyms, advanced metering systems, all of these add up in order to support the operations and the stability of power delivery and optimal power delivery to the customer. In order for it to operate without disruption to the end customer and with optimal cost to the end customer, it has to be supported with sensors and remote terminal units at the substations and at the customer side. Okay, so the markets domain is basically where the balancing of supply and demand within the power system take place. And it's basically at the outside of the or at the limits of the operations domain, and it allows us it contains all the physical assets. It basically allows for the exchange of power and exchange of services from one supplier to the other. In the market, according to NERCSIP, they consider any supplier which provide more than 300 megawatts to be a bulk generation. And considering that there is distributed energy resources, or DER, that are providing power in the market, they would have to be aggregated together in order to be part of this bulk generation and bulk power providing power to the markets when the market required. So the service providers, which basically provides the functions that support the business processes and power production and distribution and customer billing, is an emerging domain. Basically, in the old days, or in the traditional way, it used to be the billing of customers and the account management of the customer. But we're seeing more and more advancement in this area. For example, home energy generation and production, photocells on top of the building or on top of the homes that provide power, that's being handled by these service providers that are working with the rest of the markets in order to manage the requirements of the end users or the customers, working also with operations requirements and with the rest of the other domains in order to have reliable power supply to the end customer. As we've seen in the model, the biggest piece or one of the biggest pieces is the substation, and the substation design and maintenance is very challenging. The main job or the main task is to try to strike a balance between reliability, cost, and expansion. So the idea is to achieve reliability with the least cost and also allow for expansion to meet future needs. The challenges that will meet a designer and the maintenance team is: where is the placement of the substation? Is it near the consumer, away from the consumer? What is the impact to the earthing of the substation? What's the environmental effect? And also the main parts to be used in the substation and to be replaced in the substation, to be maintained in the substation. That would include your CTs, current transformers, voltage transformers, or PTs, sometimes referred to as your capacitor banks, your circuit breakers, switches. This all play part transformers. This play part of the primary infrastructure that is maintained by the utilities. For hundreds of years, the utilities maintained these primary infrastructures along with the power lines that would travel 40 to 50 miles delivering power from the generation point to the consumer point or the load point. And this infrastructure, this classical infrastructure, is overlaid by a communication infrastructure, which is the supervisory control and data acquisition infrastructure, or SCADA. The SCADA was enabled by the advent of the microprocessor. So with the microprocessor came the new devices like the remote terminal units, the GED20 and the GE relays. All of these devices basically are used in order to collect data, store the data, transmit this data to the operation point, and then some of it is being utilized data in order to take local decisions intelligently by the device. So programmable logic device and remote terminal units play a big role in trying to accomplish the replacement of a manual process that used to take place in the classical substation. As I discussed, the IEDs, or the intelligent electronic devices, are part of the SCADA systems. They're basically microprocessor based devices that collect data, store it, and transmit this data. An IED can encompass or contain more than one logical IED based on the power that's being enabled in these IEDs. So today IEDs can basically emulate or play the role of many IEDs in a single IED. So in a single physical IED, we can have protection, we can have control, we can have data acquisition. All of this is in a single IED. Basically, the reason for that is because IEDs can be today be equipped with more than one microprocessor, larger memory, physical hard disks or flash drives. All of this is giving birth to the intelligent IED devices that are occupying more than one function or complex functions. At the same time, they are capable of emulating a lot of logical devices. The IED devices communicate to each other using protocols. Protocol is a structure of a message transmitted from one IED to another IED, and that message that's transmitted would carry stored data that's collected in one IED. That stored data hopefully will go to the next IED, eventually to the operator, and the operator would decide if there is an action required, and if an action is required to be taken or a person needs to be dispatched to site, then the operator will take the right action and dispatch somebody or send a telecontrol from the dispatch center. Okay, so the protocols is a major important piece in a substation. Unfortunately, classical design of the substation did not give the protocols a great attention because of the limited choices in the market. So as manufacturers were emerging in the market, as the manufacturers were putting these microprocessors in the market, the utilities had little choices as to what is the proper device to be used in their area for their substation. The supply was not very competitive. So the utilities and the markets started to consume these devices in the substations, and the devices would carry a proprietary protocol. So for example, Conatel, Harris, CDC, there is about 400 or 500 proprietary protocols that existed from the time that microprocessors were introduced into the market until the time that open protocols started. So when open protocols started, we started to have distributed network protocol. That was created in 1993. It was introduced by GE Harris, formerly known as Westronic, and then it was adopted by the DMP3 body and was distributed to the world. Also another set of protocols that is very common as open protocols is the IEC 6870-5-101, 103, and 104. These open protocols started the object-oriented era, where instead of dealing with a piece of information that's generated by a sensor as either digital input, digital output, analog input, analog output, or counter, the information was bundled together. So I would define a capacitor to be a whole bunch of analog inputs and digital inputs. So if I put a couple of digital inputs and analog inputs and maybe a digital output, that would be a capacitor object or a transformer object. These objects were then used and packaged inside these protocols in order to transmit not just a small data. And the reason for that is because technology also advanced. So instead of communicating over serial communication, now we have the advent of the network communication, which can basically allow us for a higher bandwidth of communication. So that's where the protocols were advancing from a closed or a proprietary protocol to an open protocol. Beyond the open protocols started to appear the requirement of the utilities to go to upstream and downstream devices. So you've got the the collector or the gateway that's collecting information from all the bay controllers, and all of these are utilizing the protocols. But what happened is that there seemed to be a need or a requirement for a system, not just a protocol, a substation system that is not just defined by one of the vendors or one of the competitor suppliers in the market, but a system that's defined by an outside body like the IEC body. And that gave the advent of the 61850, which hopefully we'll discuss in the upcoming sections.
Power can be generated from many different sources. GE's electrical balance of plant solutions works seamlessly across a broad range of applications to get power from the source of generation out into the grid. Turbines and generators are at the core of power plants. They need advanced monitoring, protection, and control to ensure optimal performance. GE motors and drives enable the auxiliary processes throughout a generation plant, and our advanced monitoring and control solutions help maintain process integrity. Our advanced communication solutions, including wireless and wired, enable an intelligent and connected power plant. GE's energy management systems provide real-time visualization and control of critical electrical processes through our advanced protection, communications, power quality, and metering devices. Generated power is evacuated into the grid through high-voltage substations. GE's electrical equipment, including transformers, circuit breakers, and gas-insulated switchgear, integrates with our advanced monitoring, protection, and control solutions to ensure reliable and efficient power. GE's intelligent controls, visualization software, and electrical equipment work together seamlessly throughout generation facilities to ensure the highest levels of availability, sustainability, and efficiency. A generator sends power to this transmission substation. It passes through a step-down transformer to decrease the voltage level so it can be split into 8 circuits and evacuated to over 1 million customers. Key components of the substation include the transformers, bus, circuit breakers, transmission lines, and smart controls. When power system abnormalities occur, such as a power line fault, it poses a significant threat to the integrity of the entire system, which can result in lost power and revenue for millions of customers. The power system is mission critical, so the key components of the substation are connected to smart controls and sensors. These devices monitor and protect against system abnormalities in as fast as 20 milliseconds by using advanced algorithms to analyze the electrical signals. Key operational data is sent to the grid control center over a rugged and secure communications network. The utility uses this data to maximize the efficiency and reliability of the grid. Power systems used to be simple, with power flowing one direction from generation through transmission and distribution networks to the end power consumers. Today's power systems are much more complex. Cities and industries keep growing. Electric vehicles are being charged. Small wind and solar generation sources are plugging in. Transmission and distribution networks are becoming overtaxed. Large new generation facilities are being added. When a fault occurs on a complex grid that doesn't have advanced solutions, it can cause large-scale power outages that affect large regions and many customers. Today's systems need power and information to flow in both directions. With advanced solutions, utilities can design, protect, automate, control, monitor, and diagnose the grid. GE Digital Energy offers advanced power system solutions from generation all the way to the end power consumers.
Thank you for attending the Classical Substation Design. I hope that through this course you have reached to your objectives of learning. Basically, we started with talking about the history of electricity of substation design from a competition from AC and DC, and then how it all standardized on AC current, and how we started to see different type of generation based on the source of energy, different sources of energy, and the different substation type from generation to transmission to distribution, and the end customers could be either a commercial, industrial, or residential consumer. We covered a little bit about the protocols, the communication, and hopefully in the future courses you will see more of in-depth coverage of communication and how the modern substations are being designed. At this point, I hope you have sufficient knowledge that satisfied your requirements. If you have to do a test or an online curriculum requirement, please go ahead and do your online curriculum. Hope to see you in future courses.